Catchments for the past 10 years and has gained quite a deep understanding of our river systems and working on water quality projects in the region. And today he's going to put into perspective the vast amount of sediments that we lose through stream bank erosion and provide us with some really cost-effective options on mitigating that erosion and managing stream bank erosion. So quite relevant, quite interesting, and fits in really well with the topic of soil health. So let's welcome Chris Dench. Please put your hands together.
Thanks, Julia. Afternoon, everyone, and thanks for your time today. So I'm going to pull everyone out of the paddock and out of the soil health sort of presentations that we've had this morning. They're really great presentations, and jump into some soil conservation, particularly with regards to stream banks. So as you're aware, erosion is a massive problem, whether it's overland hill slope erosion or sort of subsurface erosion, whether it's gullies or stream banks as well. So in Mackay with Sunday, we've been doing a lot of work within the stream, looking at different options to stabilise the stream banks and prevent the loss of a lot of productive agricultural land. We've been hit by a number of large events since Yului and Debbie, and then also the monsoon trough as well. So these have really driven a lot of stream bank erosion in the region. So really trying to look at ways in which we can build resilience into these systems and try and offset any future stream bank erosion. So the water team within Reef Catchments, there's a bunch of us that have been delivering these projects. So Brendan, Carla, Amanda and Carlos have all been working together over the last few years and delivering these projects. And part of the presentation today is hopefully trying to answer some of the questions, the common questions that we often get asked about why some things aren't generally best practice or ways we go about trying to improve the resilience. So hopefully you get something out of it. So I just wanted to cover off on the natural movement of rivers. So rivers move naturally. Erosion is a natural process. Talk about sediment transport and why it's important, particularly to the reef and the size of the sediment that we're generally looking at. Two important variables in terms of stream bank erosion, slope and vegetation. So I'll just touch on those as well. Addressing the cause, not always the symptom as well. So often we've gone into rivers and really tried to stabilise a bank, and that's been addressing the symptom, but doesn't really cover off on providing long-term outcomes to address the symptom, the cause rather. And then finally, I want to just touch on Reef Trust 4. So Reef Trust 4 is a project that we've been delivering since 2017, looking at cost-effective options to reduce stream bank erosion. So I just wanted to introduce this relationship or this concept to you. I'm not sure if you've seen this before. If you know this well, hopefully I can do it some justice. So Lane's balance. Lane was a hydrologist from the United States, done a bunch of work in the rivers, and he came up with this balance effectively which describes the relationship between discharge and sediment transport capacity. So on the right hand side here we have stream, so this is stream flow, so the amount of water that will be in the channel at any one time, and we have along the top here stream slope. So all rivers are essentially the same, they're gravity and water, but the variables come into play, sediment size, the cohesiveness of the channel, the bed and the bank, and also the position within the catchment. So essentially, at its most broken down part, all rivers are technically the same, and they are just water and gravity. So with Lane's balance, essentially, if you increase any of one side, it'll either degrade or aggrade. So if for example you get a big flood event that increases the stream flow, the balance will shift to degradation or erosion within the stream channel. within systems, the balance just generally moves back and forward each year. It'll aggrade, degrade, but then it's with these larger events that really drive widespread erosion or degradation. So I'll introduce another variable later on in the demonstration, but this is a really important concept for trying to understand rivers and river management. So rivers naturally move. Erosion is a natural process, but it's been useful. It's formed all of our floodplains that have been farmed and provide food for us. But it is a natural process, but it has been accelerated since pre-European times. And a lot of that's to do with the clearing of vegetation, and a lot, Lovett and Rice actually suggested that Australian streams, the sediment load has increased by 10 to 15 times. So if I go back to Lane's balance, you can, with the sediment in a system that's coming in from either stream bank erosion, gully erosion, hill slope erosion, there's a certain amount of capacity within the stream flow to move that sediment. If it's in balance, it'd be able to move through. However, if there's not enough sediment within the supply for the size of the event that comes through, the stream flow will look to get it from the banks. So generally you need, there's always going to be sediment within the system, and it's the ability of the stream to transport that sediment, which is a natural process. And stream bank erosion is generally accelerated when vegetation along the stream bank is poor. The stream bank soils are erodible and not confined by bedrock outcrops. Where the stream channel has widened or deepened on the outside of meanders, so generally you'll see a lot of erosion around the region. The predominant source of it within the stream banks is coming from outside bends and meander migration. Disturbances such as gravel and sand extraction drives stream bank erosion. So there's been a number historically of rivers within our region where we've extracted sand and gravel. The Gregory River is a good example of that. And really the river's trying to adjust itself to get back into balance ever since. And any point affected by the size and the peak size of the velocity of the peak flows. And I'll touch on that a little bit later. However, while rivers are constantly moving sediment and transport, they're eroding the banks, a lot of this suspended sediment and the bed load actually drops out within the channel. So before it reaches the marine environment. So under a lot of the projects that we've been doing, we've been capturing a lot of LiDAR data. So LiDAR is essentially a laser map of the terrain of a catchment. So we have LiDAR captured, and then we can compare it to different time series of LiDAR. So this is actually LiDAR captured over just 2 years, 2018-19, so with the monsoon trough. So the red you can see is erosion, and the green's deposition. So there's a fair amount of sediment that's being deposited within the channel, but there's a fair amount of being lost from the bank as well. However, the main problem is that the fine sediments within what's being eroded is moved out into the marine environment. So the projects that we've been delivering is really looking at fine silts and clays. So the sediment that's below 20 microns, that's 0.02 of a millimetre. That is the soil basically that can get transported out to the marine environment quite a distance. As part of these projects, we've also been doing a lot of soil sampling, so looking at stream bank, looking at the proportion of fines, particle size analysis, and generally, depending on the underlying geology, that might be as low as sort of 17%. It might be a lot higher depending on where it is in the catchment as well. Really using that to prioritise some of the sites that we've been working on as well. So why is it really important? Obviously we've seen some of these flood plumes before. It leads to increased turbidity, which reduces light for seagrass and coral, which is then again reduces their rate of growth. So Water quality is trying to improve water quality just so that some of these marine ecosystems have a greater chance or a greater resilience to be able to settle out, and it can settle on some of the corals and smother the seagrass beds as well. So it's really quite important to try and reduce erosion and wherever the source. But in our region, we've mainly focused on stream bank erosion within the water team. So with Lane's Balance here, we've introduced vegetation. So really trying to improve the bed and the bank resistance. So the more vegetation along the bed and the bank, the higher the resistance, through to the less vegetation on the bed and the banks, the less resistance it is here. So if you improve the amount of vegetation within the bed and the banks, really try and improve your riparian zone and in-stream vegetation, it'll provide higher resistance, which then means it needs a larger flow to be able to erode. So generally, hopefully, that balance doesn't swing towards erosion and we're not losing any additional banks. This, some of you may recognise this stream. This is a good example of an increase in slope. So the photo on the left-hand side here is 1984, and the photo on the right is, 1964 on the left and 1984 on the right. So you can see an avulsion of the floodplain, through the floodplain. The downstream is at the bottom here, the upstream used to flow, big meanders, and when you have a lot more length in the stream, it has a lot less slope, a lot less erosive force acting on the river. So the longer the meanders within your creek system, the less erosive force it has. A large event came through and basically just pushed straight through the floodplain and has essentially reduced the distance from point down here to a point up here, but it's the same elevation change. It's just taken less time to get there. So really increasing the slope increases the velocity and the stream power of the channel and has formed an avulsion straight through the floodplain. So you can actually see this occurring, you can see it happening. So there's been a lot of scour here, so probably, and if you go back and look at some of the historical aerial imageries from this site, you can see it happening over time, and there's just a reduction in floodplain vegetation, and the river's essentially just trying to find the fastest path from point A to point B, and unfortunately it's come straight through the floodplain here. Another example, this was a creek system we've worked on. So the blue line is 1954, so you can see there's a lot of meanders in the creek. The time to get from upstream in the bottom here to downstream at the top, it takes a lot longer. It's got a lot more meanders, and sort of over the course, the red line is 2018. You can see there's a lot of meander cut-offs, so it's come straight through the floodplain. Another one there, another one there, another one there. So it's really shortened the length of the stream. So this stream was reduced by 21%. I think it went from about 2,100 metres down to about 1,600 metres. And then because you're increasing the slope from upstream to downstream, you've increased the velocity of the water, the stream power, its potential, its capacity to be able to move sediment. And so it's been taking it out of the stream bank. So the channel's actually widened by 35 metres in sections of this creek. So really some engineered options were basically the only solution to try and stabilise this creek line. So possibly a good point to note, and you'll be able to, for anyone with waterways through their property, there's some good resources. So if you jump on Google Earth Pro, and you can measure your bank over time. You can go back in time series and see where it was 15 years ago as opposed to where it is now, and you can work out some rough volumes in terms of what's been lost. But if it's losing generally more than a metre from the top of bank backwards per year. Some structural works may be required, but that needs to be over an extended period of time too. Often events come through and might take out 10 metres, but it's not likely to happen again, either due to the bed or the bank sort of stability, what the toe's made out of. So just a couple of examples of some of the work that we've been doing. So the top example here, we had a vertical bank. We put in a rock toe, reprofiled and revegetated. So that work was done in May 2019. So you can see how well, given the chance, vegetation will establish. And this was just recently completed just the other week. These are groin structures as well. So trying to add some geomorphic units into some of the designs that we're doing as well. The good thing about I'll just go into another couple of options that we've been putting in recently. So pile fields, you may have seen some of the pile fields around the region or heard about these. Effectively looking to put in logs. We use ironbark in rows, pointed downstream to shed any debris that sort of comes through and revegetate densely within them. The piles are 50% porosity, so a pile that might be 300 millimetres will have a 300 millimetre gap between the next pile. They allow water to pass through them, which slows the water down as it moves over the bank, but all of these structures don't address the underlying cause, which is straightening of the channel and not allowing the river to move. On the bottom here we have, these are log jams that we put in the O'Connell River, so looking to address some of the habitat value as well. So pile fields don't provide any habitat value. They do really well stabilising the bank, but with log jams you can get habitat value. They create deep pools for fish, especially during the dry season as well. And then there's also options where you can include both of them. So we have groins, and we also have a pile field through here. So what we're hoping will happen, this has all been revegetated now. This is just a job that we finished this year. The old channel runs along the back, and the river has been pushing across this floodplain for quite some time. So we're hoping the groins will push the channel back into the old low flow channel, and these piles will agrade over time and eventually build up the bank and make the low flow channel the main channel again. So there's a range of options, but a lot of the time they only address the symptom and not the cause, and they're really expensive too. So as you can imagine, the amount of rock, excavators, timber piles, and then getting them in the ground too, so then the revegetation. So it all adds up. But maybe if you do have a significant stream bank erosion on your property, just have a look at it and see what's happening. This bank here, came across this and thought, geez, this is going to take some work. But on further inspection, it moved probably 10 metres in Cyclone Debbie. But what it exposed was a really hard underlying clay layer. So indurated clay, it's almost like stone. So we had a rethink, and basically we just revegetated this whole area, put an organic blanket on with seeds and everything in it, so hopefully that comes up and stabilises it. But really we're just looking to try and stabilise the top bank, putting in a good buffer of riparian, native riparian vegetation, and now we're just monitoring it. So it doesn't always necessarily require a hard option, even if it looks pretty tragic. So I just wanted to touch on the role of vegetation. You're probably well aware, and you would have seen this type of graph, this curve recently with COVID. Everyone was talking about flattening the curve and the importance to flatten the curve. With riparian vegetation and also floodplain vegetation, it stops, it prevents the peak discharges within the channel. So if you think about lanes balanced with stream flow, the more this stream flow here would be significantly higher than what it is down here. So the longer that the flood can be delayed from getting into the channel, the reduced stream flow, which reduces stream power, which reduces the ability for transport of sediments, particularly from the bank. So riparian and floodplain vegetation is really effective at slowing the water down as it enters the stream, and can also slow it down as it comes out of the stream and into the floodplain as well. So it's really important to still get inundation of the floodplain, provides a lot of nutrients and soil for the floodplains, but you don't want it ripping through at a great rate of knots as it's going to scour and potentially cause an avulsion. So while we want to slow the floodwaters down, it results in a longer inundation. So you have a longer flood period, but it significantly reduces the peak, so much better for stream bank erosion. With regards to riparian or vegetation programs, the vegetation needs to be structurally diverse and age class diverse as well. It's no good having all mature, well-established trees and no ground cover, or no intermediate sort of trees and shrubs as well. They provide multiple levels for interception of the rainfall during our hard rainfall events, and also, so they provide that above ground and then also below ground as well. So when you have ground covers, shrubs, trees, they have a structurally diverse root system, and they all map together to really stabilise stream banks and prevent any ongoing erosion. And these good riparian zones provide benefits both upstream and downstream as well. So native seed sources being transported downstream, and also backing water up, slowing the peak discharges downstream as well. So provides many benefits. And this has been studied over a long period of time too. There's been lots of studies, so a study on the Daintree up north. So erosion rates with banks of riparian vegetation on the Daintree were 85% lower than banks without riparian vegetation. Ross Hardy did a really good study on Victoria, just indicating that the erosion from non-vegetated banks was just significant compared to vegetated banks, and it goes on. Cattle exclusion as well, orders of magnitude of differences when cattle are fenced out of riparian zones with ground cover. So really the benefit of riparian vegetation is significant for bank stabilisation, and there's also many co-benefits as well. So improved water quality, cooling the water down, improve habitat structures. So it's really, really important, and they provide a lot of benefit. So this is just a conceptual sort of visualization of riparian revegetation projects. So over time we have the rehabilitation effort on the y-axis there, the time, and then the resistance or the critical share of that provided by that riparian structure as well. So over time, initially the revegetation effort is high and drops away over time, and the strength or the bank stability provided by that revegetation increases and grows over time. You can see there that this is a 30-year time frame, but within our region, we're pretty blessed with with the ability to grow. And so this site here, we planted this in May 2019, and this photo's from July, August 2020. So given the right conditions, we had irrigation set up, and we mulched the soil as well. The vegetation has just jumped out of the ground. It's probably been a 90-95% survival rate, and it's just, it's connected to lots of riparian vegetation. It's been really, really successful. Okay, I just quickly want to touch on the Reef Trust 4 project. So Reef Trust 4, we're looking at ways to reduce sedimentation to the reef. It's an Australian government funded project, and looking at gully and stream banks. So in our region, Mackay Sundays, we're only working on stream banks. It's looking for continuous improvement in capacity to be able to manage the issue, ensuring long ongoing maintenance and management of these sites, It provides science and technical support to delivering the project. So we have CSIRO and Griffith University providing technical advice to projects. And it's really about demonstrating cost-effective gully and stream bank stabilisation projects. In the Mackay-Whitsunday, we're only working in the O'Connell Basin, so that's the O'Connell River, St Helens Creek and the Murray Creek. And we're developing reach scale approaches. So rather than just addressing the symptom, so looking at a bank and stabilising that bank, we're trying to build reach scale proposals to deal with some of that stream power and reduce erosion. Again, we're only looking at the fine fraction, so 20 microns, so really only that really small sediment which is being transported long ways. And we need to develop projects that are less than $500 per tonne of fine sediment saved. And how do we do that? We look at basically the sediment savings equals the baseline load, so how much has been lost from that reach over time, or how much has been lost from the site, multiplied by the effectiveness of the treatment, and then multiplied by the delivery ratio to the coast. How often or how much of that sediment, that fine sediment that's locked up in the bank, how much is being delivered to the coast. Within the O'Connell Basin, that's anywhere between 90 and 99% of that fine fraction has been delivered to the coast. So to date, we've developed 4 reach scale projects, 31 project sites across 29 properties and just the 7 engineered structures. In the last 2.5 years, we've planted 40,000 native trees and with an 84% survival rate. Also eligible is riparian fencing, and the total expected sediment savings from the project is 7,500 tonnes of fines per year. So just as an example, this is Murray Creek. We commissioned these LiDAR or reach scale reach summaries. So we had LiDAR flown in 2009, which is a state government data set. We flew it in 2018 and overlaid them, compared where a lot of the erosion was and what sort of losses there were. So along the 18.5 kilometres of Murray Creek, there was 720,000 cubic metres of stream bank erosion over a 9-year period. So that provided us with our baseline loads. With the sites, you can see here that some of the sites are kicking well above average. This little inset floodplain lost 45,000 cubic metres. There's 11,000 there. So there's some hot spots within it as well, and that makes up the 140,000 cubic metres from hot spots. So within the Murray, we also had a look at some of the erosion and where it was happening, and meander migration. This little pie chart down here was the dominant erosional process that was happening. So with the project, we've worked with 15 project sites with 8 landholders, planted nearly 16,000 trees over the last 2 years, 4 kilometres of fencing, and we've implemented 5 structures in the Murray. So initially what we did was we looked at the creek and we looked at the different reaches within the creek to be able to develop up reach scale proposals. So this is just a lower to middle reach. You can see all of the different erosional processes that are happening. We've got some meander migration and point bar development. Again down here, we've got a meander cutoff, so an avulsion straight through the middle of the channel there. We've got some lateral migration, and then also these meander developments as well. And there was an avulsion risk straight through here. So this was going to straighten, shorten, and unfortunately cut that paddock into an island in a much smaller paddock. So working out the sediment savings, so our baseline yield times bulk density times the proportion of fines gave us the baseline yield. With the effectiveness, we look at the effectiveness of engineered structures is considered 40%. Revegetation is 20%, so that's saying it will reduce erosion by 20%, and then fencing as well is 10%. Delivery to the coast for this particular was 99%. The cost of the engineered structures was $900 a tonne $900 a tonne of fine sediment saved. So pretty costly, but the average cost of the revegetation for fine sediment saved was $260. So it demonstrates that it is a cheap option to be able to really try and address the cause of the issue there. So just quickly, this was all of the project sites that we had up. So a couple of landholders had a number of sites, and there's probably 3 of the 5 reaches included within this project. So a reach here, and a reach down here. So total project cost for the Murray Creek project was $840,000, and the expected modelled sediment savings is 2,400 tonnes of fine sediment saved at a cost of $340 per tonne of fine sediment saved. So pretty good value for money, mostly focusing on the revegetation, but where it's required, needing to do the large engineered structures as well. So just some key points. Structurally and age class, diverse riparian vegetation is the cheapest and best defence against streambank erosion. If you do want to jump on, you can jump on lots of good platforms. So Google Earth allows you to go and have a look at what's happening upstream and downstream. If you use some of the time series, you can go back 14, 15 years. Q imagery was another good one. You can go back and look at imagery from the Queensland government back to the 1950s, and you can really see how a lot of these streams have changed over time. And just finally, addressing the cause and not just the symptom provides a longer term outcome, and prevention is a whole lot better than the cost of a cure, and it doesn't also shift some of the problem upstream and downstream as well. So just some useful resources. The Reef Trust 4 has a gully and streambank toolbox that you can jump on online and dig into some of the guiding principles there. Principles of Riparian Land Management is another good resource. Queensland Soil Conservation Guidelines, so that has information on streambanks for a couple of chapters, but lots of useful information. And keep an eye out, Queensland River Management Guidelines. These are currently in draft form, and they should be released in the next, hopefully, 6 months. But they have some great information in there for anyone interested in streambank management. Thank you.
They need a bit of help. Any questions around streambank erosion or any type of erosion that you come across on your place? Dave, Hunter, yes?
Just a comment, Chris. Did you do any work on how much fine sediment is contributed by bare fallow cropping land during the summer, and how this might be addressed using regenerative practices?
I haven't, Dave. I'd have to go back to probably the 2008 Water Quality Improvement Plan, and I think that generally says that it's losing about 1 tonne per hectare per year. I think that was sort of worked out well, and John did back then, but yeah, we haven't done any recently, sorry. Alan?
Chris, I noticed on a few of those slides you had up there, that a lot of those creek banks that were severely eroded had no remnant vegetation at all left on them, like they had been cleared right up to the top of the creek bank. Is that the case?
Often there is vegetation left, but doesn't provide the structural diversity that's required to really hold it together. There needs to be a good mixture of ground covers, larger trees and shrubs. And I think historically there's been some land management practices, whether it's burning or not fencing off riparian zone and things like that, which has really sort of exacerbated the problem. Additionally, I know a number of locations where cyclones have come through and really knocked over that riparian vegetation, and then it takes a lot of work to get it back up. But I'd argue that it's really important work. Michael?
Yeah, Chris. A lot of this work would help if we could get funding to stop the water getting into the creek in the first place. Surely it would be cheaper to regenerative farming or something like that, to do the cause and not the symptoms.
Mm-hmm. Yep. Yeah, and I mean we've put in projects to be able to try and do that sort of stuff as well. But yeah. No. That's right.
Yeah, I think my question was a bit similar to those last couple. There was a lot of mention, I don't want to take away from the great work he's doing. The elephant in the corner for me is you say that you're addressing the symptom, or the cause rather than symptom. There's no more rainfall. It's the same as it was 100 years ago. We've got all these issues. Yeah, is it an infiltration problem or is it a creek problem? I think we've got to get outside the creek a bit. A similar question.
Well, yeah, I think you're right. So there was a lot more, obviously 100 years ago, there was a lot more vegetation within the floodplain, which was intercepting a lot of that rainfall. And the riparian zones, the buffer zones, were a lot thicker as well. So with those sort of reducing those peak discharges, slowing the water down before it can enter the creek and cause those high peaks, has really led to a lot of the stream bank erosion. Bob?
I think you missed the point with what Paul was trying to say.
I'd like you to speak up. Here you go.
I might be being a bit rude, but I'll just clarify what I understood Paul to be saying is infiltration. And we're getting away from here a bit, but there's lots of data on that now. Gabe Brown and there's a number of blokes in America have demonstrated the differences. And some of you blokes not going to like it, but cropping country, and I'm talking broad acre cropping country, 2 hours to get a half of inch of rain to soak in versus Gabe Brown on his country with his cattle, 2 inches in 15 or 20 seconds. Different management processes, but I think that was the point Paul was trying to make. And I'll rephrase that. We get 10 inches of rain on country that won't absorb anything. That's all in the creek. You get 10 inches of rain on country that'll absorb even a couple of inches an hour. You might have a third of it in the creek. I think that's a real important point.
Yep.
So, well, coming back to, dealing with compaction issues and finding solutions through the regenerative farming. Have we got any other final questions? Oh, Jonathan. Yes, thank you.
Just on where you've got erosion on one side, do you find on the other side it's like you got building up?
It depends on the erosional process, what's happening. So whether the creek is widening and there's lateral migration, that won't necessarily relate to, might happen on both sides. Certainly on meanders, you get the point bar development, and there's been a lot of work looking at, does the point bar drive the erosion or does the erosion drive the point bar?
Yeah.
And I think it's the latter.
Yeah, that's what we find. It's what's happening upstream.
Mm-hmm.
So we'll get build up, and then that becomes before the erosion.
What was that, sorry?
We'll get it'll build up.
Yep.
Before then like next year, it'll erode the other side.
Yeah. Yep. Yeah, it is tough, and it's meanders the dominant driving erosional process. And historically, there's been a lot of excavation of the channel, but that's generally just proven to increase stream power and then sort of drive erosion either downstream or whatnot. It is a real challenge, and there's been I'll go out to lots of sites all the time where that's happening. So I think depending on how fast it's happening and what you can do about it. So that's why I think prevention is better than a cure. So really trying to make sure that the riparian zone is able to buffer against that, and then you won't get the point bar pushing it across.
Yeah, yep. So and where it's built up, it seems to we'll get a lot of tree growth, and
yep,
it'll self rejuvenate. have you done anything in trying to like stop that from happening, like cutting trees down actually?
It's not considered best practice. So there's erosional within the creek and there's transport capacity. So a lot of the time those islands and bars that get built up get pushed through. But you're right, in terms of islands that establish and then the trees that actually pop up, but that's generally considered the river's trying to heal itself in terms of slowing the water down, because those bars, those geomorphic units, the vegetation actually are doing a job to slow the water down as it moves through. So it's yeah,
like I know what you're trying to say, yeah, because we found the more growth you get, then the more build up, and then the more it erodes on the other side.
Yeah, yep, and it's the river trying to put some length back into itself, which is not great for us. But I mean, these rivers have evolved over thousands of years, and we're, our footprint's only a couple hundred, so it is.
Yeah, a lot of the places we see where it erodes, you can see the old riverbed, Yeah.
Yep. Yeah.
So, and then you usually got a sandy bank, which erodes quite easily.
That's right. Yep. Yeah. No, it's certainly a challenge, and it's a big challenge, but I think trying to work over larger stretches of the creek rather than just single sites, and they're really just trying to get the vegetation. If the bank is migrating at sort of those consistently more than a metre a year, might require some structural work, and you can do that relatively easy on a meander. The pile fields work pretty well, particularly on sandy banks as well. But yeah, it's a challenge, and it's expensive.
No worries.
Yep, cheers.
Thanks, Chris, for such a comprehensive overview, and thanks everyone for your engagement as well. It's Graeme's turn again. He's very keen. Look at him, up already. Let's stretch our fingers, get our notepads out, and get ready to take lots of notes.